Have you ever actually thought about what's going on right above your head? I mean, really looked up? The sky isn't just some static, pretty blue background. It is a literal, churning factory of violent physical transformations. We're talking about an arena where invisible water molecules are performing this high-stakes, chaotic dance that, believe it or not, completely defies our absolute best supercomputers.
It brings up this wild paradox, right? Why on earth can we map out an entire century of global climate change with incredible mathematical accuracy, but we completely failed to predict if it's going to rain on your head exactly 60 minutes from now? It's mind-blowing. And here's the thing, it's not a failure of our radar equipment. Not at all. It's a fundamental property of chaotic, microscopic fluid dynamics. We're dealing with an environment so unbelievably volatile, it challenges the very laws of physics as we know them. I mean, think about this. You can have a kilometer-wide parcel of air floating right above your city, and it's sitting at 400% humidity. 400%! And yet that massive, invisible, saturated sponge can just outright refuse to drop a single drop of water. It just holds onto it, suspended in this impossible tension, waiting for a trigger.
And that brings us to Section 1, the Great Precipitation Paradox.
So what exactly is that trigger? Well, the invisible catalyst required to snap that tension is entirely microscopic. Every single drop of rain that has ever fallen on you in your entire life required a tiny seed to exist. Scientists call these cloud condensation nuclei, or CCNs. Sounds complicated, but they're basically just microscopic specks of everyday dirt, dust, or even sea salt. Without these tiny invisible impurities, a cloud is literally just a giant void of trapped, useless gas that will never ever fall to the ground. To really wrap our heads around this, picture a middle school dance or maybe a wedding dance floor. The water vapor molecules, they're the guests. They are packed into the room, they are full of pent-up energy, but they're incredibly shy. You know the type, they just hug the walls, way too timid to start dancing on their own. Now the cloud condensation nuclei, that microscopic dust and salt, they are the professional breakdancers who suddenly kick the doors open and jump right into the absolute center of the room. Instantly, they provide a center of gravity. The shy water molecules finally have something to latch onto. They organize around those professionals and boom, the collective raining dance begins. But without the dancers, absolutely nobody moves. So, how does this actually build into the invisible genesis of a cloud? Well, it all starts with something called adiabatic expansion. Sounds like a mouthful, but here's what it means. When a pocket of air rises up from the Earth, the atmospheric pressure around it starts to drop. This allows that pocket of air to expand, and as it gets bigger, it cools down. Eventually, it hits this exact, critical moment, the dew point transition. It is the exact threshold where a gas is literally forced by the laws of thermodynamics to transform into a liquid droplet. But here's the catch. Whether it becomes just a gentle, misty haze or a violently intense storm depends entirely on what it bumps into next, which zooms us out from a single microscopic droplet right into the chaotic, turbulent environment of a forming cloud. It's an absolute battleground up there.
Which perfectly segues into Section 2, the bake sale battleground.
Imagine the most chaotic bake sale you've ever seen. You have exactly one single tray of cookies, and that tray represents all the available moisture in the air. Now, if you have a highly polluted sky packed with 10,000 microscopic aerosol particles, it's exactly like having 10,000 greedy customers fighting over that one tray. Everyone gets a tiny microscopic crumb, nobody is actually satisfied, and those resulting water droplets are just way too light to ever overcome gravity, so they just hang there. You get this long-lived, depressing, hazy cloud that completely refuses to rain. But take a pristine, clean sky with only 10 customers. Each particle gets a massive, huge slice of dessert. They gorge themselves, they get incredibly heavy, and boom, they immediately fall as rapid torrential rain. The difference is literally night and day.
Okay, so the truly crucial point here is what happens when that vapor finally actually turns to liquid. It releases something called latent heat. This is this crazy, invisible energy that was just stored up during evaporation. When condensation happens, that heat is suddenly unleashed all at once. It acts exactly like a revved-up internal combustion engine right inside the cloud. It warms the surrounding air, makes it violently buoyant, and creates this runaway positive feedback loop. This hidden engine is literally what explodes a tiny, completely harmless little cumulus puffball into a stratospheric, terrifying cumulonimbus monster. And inside that monster, it is pure, unadulterated chaos. It's the engine of tropical rainfall, and it functions exactly like a brutal game of gym class dodgeball. Meteorologists call it collision coalescence.
Basically, you have these massive updrafts sweeping up the smaller, slower droplets. But meanwhile, the larger, heavier droplets are falling super fast. So, they violently collide in mid-air. The big, fast droplets literally absorb the smaller ones, growing exponentially larger with every single impact, until they become this massive singular target that is entirely too heavy to stay airborne. And then, they plummet. Down comes the rain. But hey, tropical storms are really only half the story here. Because as we move to colder latitudes or higher up into the atmosphere, the rules of the game change entirely.
Let's move on to Section 3, the ultimate meteorological heist.
This right here is called the Bergeron-Findeisen process. And I kid you not, it is the ultimate meteorological heist. So inside these freezing clouds, you've got supercooled liquid water and solid ice crystals, and they are living right next to each other. But there's a catch. The physical vapor pressure over ice is actually lower than it is over water. The atmosphere is desperately trying to seek equilibrium, and to get it, it literally evaporates the liquid droplets just to feed their moisture directly to the ice. The ice crystals act like ruthless thieves. They drain their liquid neighbors completely dry, growing incredibly fat and heavy in the process. And once they hoard enough stolen mass, the entire system just collapses under its own weight, crashing down to Earth as a heavy snowstorm or freezing rain.
Trying to track all of this micro-chaos is essentially the holy grail of climate science. Today, we use these incredible dual polarization radars to scan the sky, desperately trying to figure out if these tiny particles are hail, graupel, or just regular rain. And why does that matter? Because clouds act as the Earth's primary thermal regulators. Low clouds reflect sunlight and cool the planet down, while high clouds trap heat and warm us up. So trying to predict this, what we call radiative forcing, is literally like trying to map billions of chaotic billiard balls that are constantly changing shape and size, all while the planetary pool table they are sitting on is vibrating and accelerating. So how on earth do we solve a math problem that has trillions of moving parts? Well, we have to zoom way out to the macroscopic scale.
Welcome to Section 4, Unraveling the Planetary Sweater.
For decades, we essentially relied on supercomputers making approximations. I mean, let's be honest, it was basically blind guesstimation, which is exactly why forecasts completely fail us during extreme sudden events like flash floods. But now, we are integrating machine learning. We are building advanced AI emulators to achieve what's called probabilistic certainty. Think of it exactly like a professional poker player. A poker pro doesn't actually know what specific card is coming next, right? But they've studied the historical data so obsessively that they know the exact mathematical odds of a specific hand playing out. So, we're no longer trying to track every single drop of rain. Instead, we're playing the mathematical odds of the weather itself.
But of course, humans are rarely content with just observing and predicting, are we? We are actively intervening. And that brings us to the highly debated topic of cloud seeding. This is the anthropogenic, or human-caused, injection of a compound called silver iodide straight into the sky. The ultimate goal here is to either force drought relief by making it rain, or to destroy hail before it can form and ruin crops. It is a subject of intense, ongoing scientific debate, because think about it, we are essentially tinkering with the planet's actual metabolic process. We're introducing completely foreign variables into a highly sensitive, self-regulating feedback loop.
Which leads to this absolutely chilling thought. When you manipulate the atmosphere, you risk inducing massive weather instability. Quote, think of this as pulling a single thread on a finely knitted sweater, creating an unforeseen tension in the weave that could cause the entire garment to unravel. You might pull that thread to fix a small snag in one spot, maybe to bring rain to a parched, dying farm, but you are creating an unforeseen tension in the global weave. You could very well cause the entire atmospheric garment to unravel, creating a devastating deficit of rain somewhere else entirely on the planet.
So, what's the ultimate solution here? To bridge this crazy gap between microscopic chaos and macroscopic survival, we have to radically shift how we gather our data. The future of nephology, the study of clouds, demands massive investments in global high-frequency observation networks. We need real-time, granular data tracking exactly how these aerosols interact with clouds on a second-by-second basis all around the globe. That is exactly how we neutralize the precipitation paradox once and for all.
Because when you really step back and look at the sheer scale of human scientific ambition required to even attempt to understand this, it is profoundly humbling. We have to view the atmosphere as an integrated planetary-scale living organism. We're moving so far beyond mere observation. As this quote beautifully states, we are not just predicting the weather,
We are learning to translate the language of the sky itself.
The sky is literally speaking to us through phase transitions and latent heat. It is a language of absolute survival. So the next time you step outside and you look up at a passing cloud, I want you to ask yourself, what if these silent white masses floating above us are actually the most vocal, influential components of our global survival? It completely changes how you see the world, doesn't it? Thanks for exploring the sky with me in this explainer. Keep looking up.